Okay, so today we are going to be looking at Chapter 4, which is two-dimensional kinematics. The big ideas today are that motion in two dimensions will travel along a horizontal and a vertical path, and that objects in free fall are going to move under the influence of gravity alone, and that they follow parabolic pathways. And the first place I want to start is with velocity. So when velocity is constant, the motion is considered to be along a straight line. However, that motion, if it is in a straight line and there's an angle, is going to have both an x and a y component. And this is something we can solve separately. So we can take our typical equation of motion right here. And hopefully y'all keep these equations of motion near you so that you can easily refer back to them. And you're going to see it broken up into the x and the y components. So this turtle that's traveling at an angle in a straight line, its motion is going to have a value in the x direction and the y direction. We can apply that rule, that component rule, to all of those other equations of motion as well. So we can take them from their typical form and simply break them apart into a form that would solve for only the x component and a form that would solve for only the y component. And we are going to try that right now. So we have this helicopter that is traveling with a constant horizontal speed. And at time 0, it starts accelerating vertically. And we're going to assume that helicopter's acceleration remains constant for the time we are interested in studying it. So first, we're going to find the horizontal and vertical distances that it travels in 5.3 seconds. And then we're going to find the velocity components of that helicopter. Before we can do any of that, we need an image, a diagram. I'm not very good at drawing diagrams, so I just use the ones from the book so that there's not much confusion surrounding what this is supposed to look like. And you'll notice that we've assigned the XY coordinate system in the way that makes the most sense, with the helicopter traveling in the positive X direction and positive X direction. And positive Y direction. So in this problem, we don't have an angle. It says that the helicopter is traveling in the horizontal motion. And, it says there's a horizontal speed and that there's a vertical acceleration. So this is going to make this problem a little bit easier. Now, some information that we have been given, and it's always good to write this down. We know that V is 11 meters per second. And it says that this velocity, this speed in the horizontal direction, okay, so horizontal is this, I am so sorry. Horizontal is this way. That means that this velocity is in the x direction. So we should make note of that. And we also see that we have acceleration vertically. So acceleration vertically, so that's the y direction, is equal to 0.96 meters per second squared. And hopefully y'all are able to read this a little bit better today. I got a new stylus. So the first thing we want to do is find, so part A, we want to know our distance in the x direction, and we want to know our distance in the y direction. Okay, so to solve for this, we are going to need to use one of those equations of motion. But we have to work with what we've got. We have the velocity in the x direction, and we have the acceleration in the y direction. Well, let's just go ahead and start with the x direction. So I'm looking for dx. Okay. We can use the equation, and I'm just referring back to a chart. So again, have that chart and see which equation makes the most sense to use. here is what the equation looks like. Okay, and I only placed my x information here because, well, that's all we care about solving for right now, is this value. So we have one thing that we can immediately cancel out. That's because we only have acceleration in the y direction. That means the acceleration in the x direction is 0. So we can just ignore that. Well, we want to solve for x. So that's what we're looking for. And we know that this helicopter starts at position 0 because we're at the origin. And we have our velocity in the x direction, which is 11 meters per second. And it gave us our time, which is 5.3 seconds. So to solve for x, let's just do a little multiplication. And when we do, you should find that x equals 58 meters. Okay, so that's pretty simple. So y'all can go ahead and try the y direction and then press play when you're ready. Okay, so for the y direction, we're going to have to do things just a little bit differently, but we are going to use the same information. Well, the same equation, I'm sorry. So we have y equals y naught plus the velocity in the y direction plus 1/2 a in the y direction t squared. Okay, well this time we don't have a velocity in the y direction, so that goes to 0, which is going to make this equation y equals, and our initial position in the y direction is also 0, plus, and that's 1/2. Our acceleration is 0.96 meters per second squared. And again, we multiply that by 5.3, but we have to make sure to square it. And when you do this, you will find that y is equal to, and we need to use sig figs here, so it's going to be 2. It'll be equal to 13 meters. So now we know that it's going to travel 13 meters upwards and 58 meters to the right. Okay, that is part A. Now let's try part B, and I'm going to erase all of this. For the second part, we're solving for velocity. So the x and y components of velocity. So we're going to need to use a different equation of motion. This time, the equation that makes the most sense to use is going to be the one that allows us to solve for Vx and Vy. So we're going to use the one that I showed earlier, which would look like this. And we'll do Vy in a second. I'm going to let y'all do that one. So again, we know that that velocity in the initial velocity in the x direction was just 0. Oh, I'm sorry, not 0. I am so sorry. I did not mean to say that. It's 11 meters per second, plus this goes away because we had no acceleration in the x direction. This means, well, this is going to be easy to solve for Vx. The velocity in the x direction is just equal to 11 meters per second, and that makes sense because it's a constant speed. Okay, so go ahead and try the velocity in the y direction and then press play. Okay, so for that y direction, we have Vy equals Voy plus AT. Oh, and that's in the y direction. This time, we can get rid of the initial velocity component. There is no velocity in the y direction. And we'll find that Vy is equal to 0.96 meters per second squared at time 5.3 seconds. So Vy is just going to equal 5.1 meters per second. Okay, so that was one of the simpler problems we'll be doing in this unit. Now, here's some general information about projectile motion, and you're going to want to commit this to memory or at least have it available to look at when you're working problems. So, number one, we're going to ignore air resistance. Number two, we are going to assume gravity to be 9.81 meters per second squared in the downward direction, and we're going to ignore Earth's rotation. Okay, and if the y-axis is pointing upward, then our acceleration in the x direction is going to be 0, and the acceleration in the y direction will be negative 9.81 meters per second because of gravity. I'm showing you this photo because I wanted to quickly point something out. So this person is roller skating and she's bouncing a little ball up and down. Even though to her it appears that the ball is only moving up and down, if we were looking at it from afar, we would actually watch the ball travel along this pathway. So that's just a visual, a good illustration that the projectile motion in general is going to happen on a curved pathway. Curved pathway. We also have motion independence. So that means that acceleration and velocity can actually have different directions. They do not have to be pointing the same direction in projectile motion, and they often will not be pointing in the same direction. And you saw this in lab number 2, or I hope that you remember seeing that in lab number 2. So here, when we see in this case, in this second case, we see that acceleration and velocity do not equal. The acceleration is pointed straight down because that is the force from gravity. So our acceleration is in the downward direction, but our velocity shows us where it's headed at that particular point in time. So we would watch this very slowly change, like so. And we're going to practice this, don't worry. So in this particular case, we would see our acceleration in the x direction is 0, but our acceleration in the y direction is going to be gravity. Well, negative gravity. Okay. Once again, I'm showing you the equations of motion, and these are the ones that we will specifically be using for projectile motion. And you'll notice that just like in the previous section, these have been split into their x and y components. So it's going to be very important when we have something that's not moving in the horizontal or vertical directions only, that we are utilizing these equations for both the x and y directions. And to find these, you use the assumptions that we talked about before. So you would just plug in this information, and that's why these equations look a little bit different than the ones we were just viewing. Okay. Now, launch angle, we can have a launch angle of 0, or we can have one that goes up into the air. But first, we're going to talk about launch angles of 0. When the direction, so we're looking at this picture here. And if the launch angle is 0, it's going to look like this second picture. So the person will just jump straight out instead of going up and then coming back down. They're going to go straight out and then go down. So that would be a 0 launch angle. If that angle is 0, hold on, I'm sorry, I already said that. I am trying to go to the next slide. Okay. Okay, so with a zero launch angle, the initial velocity in the y direction is going to be 0. And that's because theta is equal to 0. That makes sense. So there won't be any velocity in the y direction. When that is the case, we are going to have to make a couple more assumptions. And that is that the initial x position is 0 and the initial y position is whatever the height is. So if we went back to the picture we were just looking at, it would be the height of the ladder or of that cliff. That is also very important because we can use this information and substitute it into our equations of motion. You see they did that here. That's how we got h in this equation. So you're going to need to remember that if there's a 0 launch angle, our initial x position is 0 and our initial y position is just height. And we're going to work a problem with that very soon. Now we're going to look at it on a graph. And these graphs are important. They can help us visualize, and y'all might even be asked to create your own graphs like you were in lab number 1. So when there's a 0 launch angle, the object is going to follow a curved path where the horizontal motion is constant and the vertical motion accelerates. So the horizontal motion is constant, but the vertical motion accelerates. Okay, that's going to be an important piece of information to keep in mind because that can help you to solve problems later. When you remember that the motion in the x direction is constant, but in the y direction, it will accelerate. When we are trying to solve equations for anything with a parabolic path, there's a few things we're going to want to do. And one of the first things we want to do is eliminate t from our equations of motion. So in order to eliminate t from this equation, we're going to have to make some substitutions. So let's substitute the information that we've just discussed. Okay, so at x, the initial position for x, if you'll recall, it is 0. So we're going to go ahead and put 0 in this equation. We're going to substitute that, which means that we can just rearrange this equation and t is actually equal to x divided by the initial velocity. Okay, now let's take that and substitute it back into another equation. So here is an equation that incorporates t, that contains t. And when we plug all of this information in, okay, so let's look at the substitutions that were made. In the y direction, remember that just is equal to h. That initial y is equal to h. The acceleration is equal to gravity. So that's why you see a g here. And then you see that we have substituted t into this equation. And this should have been like that. I apologize for that. With the square on the outside, it should not be on the inside. Okay, so this actually ends up having the form y equals a plus bx 2, which is just a parabola equation. So that means the landing point for this person can just be found by setting y equal to 0 and solving for x. And again, we are going to practice this. I know it doesn't make as much sense when we're just looking at variables. It makes a lot more sense when we put numbers with it. Oh, and I hope y'all can see that at the bottom. So this is actually how we would solve for x. It was just equal to the initial velocity multiplied by the square root of 2 times the height divided by g. And let's go ahead and try that out. Okay, so we have a mountain climber who is just going to jump across a crevice. And we see the opposite side is 2.74 meters lower. It's separated by a distance of 4.10 meters in the horizontal direction. So the runner is going to the climber gets a running start and he's going to jump. We want to know the minimum speed that will allow him to cross safely. So the minimum speed he needs to cross a distance of 4.10 meters in the X direction and 2.74 meters in the Y direction. So here is our diagram, just to help us get an idea of what's going on. So this climber you see here, his motion is straight, a zero launch angle. Okay, good. So we can make use of those assumptions that we just substituted into the equations of motion. We know that this distance right here, h, so h is equal to y naught. And in this case, we know that that is equal to 2.74 meters. The theta is 0, in case we need that information. Our final x position is 4.10 meters, and that initial x direction is just 0. Okay, so we're going to pull the information from the previous slide because all we want to do is figure out what this x value is. So we want to know, the speed, but in order to find the speed, we're going to have to rearrange an equation. Okay, so we saw on the previous slide that x is equal to the initial velocity times the square root of 2 over h divided by g. Okay, so we can rearrange this so we will be able to solve for velocity. And when we do that, you will find that velocity is equal to x divided by the square root of 2h over g. Okay, so now we're just going to plug in the information we have. Okay, and we know that that height is 2 times 2.74 divided by 9.81 meters per second squared. And when we solve for this is just going to be equal to 5.49 meters per second. Okay, so that's what our velocity is going to need to be in order for this person to safely jump across the crevice. And I'm about to erase this. Okay, so now let's solve for part B. And y'all are actually going to try part B. So go ahead and you'll press play when you're ready. Okay, so to solve for part B, this is pretty easy. We see that this time the climber's speed is 6 meters per second. So let's just make some substitutions and solve for x. So this will be even easier because we don't have to rearrange the equation. So when you plug all of your information into this equation, you will find that x is equal to 4.48 meters. And that will be your final answer. Okay, next slide. Now, that was all about zero launch angle, where theta is 0 degrees. Now let's talk about launch angle in general, so where theta is greater than 0 degrees. When that's the case, we are going to have x and y components. It is a given. This is going to happen. And these are going to be found the same way as in the vector chapter. So we're going to utilize this information just like we did in the previous chapter. And you're going to see this a lot, so commit it to memory. Put it on your equation sheet. We're going to combine that with the equations of motion that we've looked at. And when you do so we're just substituting this information in to the equations of motion we were just looking at. We're going to get more equations of motion, which look like these. So these 6. Okay, but these are only when we have a launch angle where theta is greater than 0. This is the graph form. So this is what we would see when theta is greater than 0. And we see that the launch takes a full parabolic pathway. And that will also be important. So we can see that. Nice parabola. And let's work another problem. Okay. So this time we have a golfer. And this golfer sends a ball over a 3-meter high tree that's about 14 meters away. The ball is going to land at the same level that it was struck, so it'll land at ground level. And it travels 17.8 meters horizontally. The ball is going to leave at an angle of 54 degrees above the ground, and it'll land 2.24 seconds later. So what was the initial speed of that ball? Well, we need a diagram. Okay, there's a lot of information here. So we see that because theta is not 0, we're going to have both x and y components. This, at any point, is going to have an x and a y component, so we're going to have to find some of this information. Okay, well, what do we have? Let's just write down a few things that we have. We can say it starts at a position of 0 and it ends 17.8 meters away. We know theta is 54.0 degrees. We know time is equal to 2.24 seconds. We know that at the end, velocity, well, the ball is going to come to rest, so velocity would go to 0, but we want to know what that initial speed is. So what does it leave the golf club going? At what velocity? Well, this part is actually pretty straightforward. So let's look at our equations of motion and pick out one that lets us use the information we have. And in that case, we have one that says x equals v naught, so the initial speed multiplied by the cosine of theta multiplied by t. Well, we have all of this information except for the initial velocity. So we rearrange this so we can solve for velocity. Rearrange so we can solve for velocity. And when you do, you'll find that that initial velocity is 13.5 meters per second. Not too bad. Okay, so for part B, we want to know how high the ball was when it passed directly over the tree. So y'all go ahead and give that a try yourselves and hit play when you think you've got it, or if you're not sure what to do, just keep listening. Okay, so for part B, let's think about the information we know. We want to know what's happening right above the tree. So let's see, right above the tree, I would say we are at a position of x equals 14 meters. But we want to know that y value because we want to know how high it was. So we want to know what's going on right here. Well, if we go back to those equations, we should be able to find one we can use. And in this case, we're going to use y equals v naught sine theta multiplied by t minus 1/2 g t squared. Okay. The first thing we're going to need to do, so we have a little bit of a problem. We don't know t. We know what t was when it landed, but we don't know what it was at this particular point. So we need that piece of information in order to continue. Well, was there another equation that would allow us to get that information? Yes, there was. And it happens to be the equation that we just used. So if we want to solve for t, we can just use the x equals v naught cosine theta times t. We know that x is 14 right above the tree. And we know v naught because we just calculated it. We know what the theta is, And we can find that t is equal to 1.76 seconds. So we can now use that information and plug it in along with all of the other information that we have. And remember, we calculated v naught in the previous part A, which is how I just calculated for time. And when you plug all of the appropriate information in, you should have found that y is equal to 4.03 meters. Excellent. Okay. And we are moving on. So now we're looking at projectile motion instead of launch angle. And projectile motion is always going to have a range, which is just the horizontal distance that projectile travels. But when the initial and the final elevation are exactly the same, you are going to find this to be true. So you're going to want to write this down somewhere as well. There's lots of equations we're going over today. And you can always use a little equation sheet on your quizzes, during your labs, on the test. I don't mind that at all. So the range is going to be a maximum at some point when theta is less than 45 degrees. For this particular item, that's true at 15 degrees. So less than 45 degrees is when our maximum range occurs. And that's all I was going to mention about that. Projectile motion also has a lot of symmetry, which makes, at least makes portions of this easier. So the velocity is going to be the same going up as it is coming down. And just make a note, this capital T right here, that is equal to the total flight time. So capital T is the total flight time. That little t is a particular time on this graph. And speed will be the same at any point that is symmetrical. So this point and this point, this one and this one, etc. And let's look at another problem. And I know I'm going through this quickly, so if y'all have questions for me or you need clarification, please don't be afraid to ask. So we're going to look at a fish who is going to try to knock an insect off of a leaf. And, this is getting complicated. And I understand that. This fish is going to squirt water out of its mouth with an initial speed of 2.30 meters per second at an angle 19.5 degrees above the horizontal. So we're at an angle again, which means we're going to have X and Y components. Well, when the stream of water reaches a beetle on a leaf at height h above the water surface, that water is moving horizontally. So that indicates that would be a maximum point. How much time does the beetle have to react? What is the height of the beetle? And what is the horizontal distance covered between the fish and the beetle at the point the water is launched? Again, I know that sounds complicated. All right, we have our image here. And again, I just pulled this from the book. It's much easier than me trying to draw it and make it so that you can understand what's happening. So if y'all will go ahead and take a look at those basic equations for projectile motion, this is projectile motion, then we can start choosing things or equations that will help us to solve this problem. So we want to know first, how much time does the beetle have to react? So we know we're going to have to solve for time. Well, we have the following information. We know that initial speed, initial velocity is 2.30 meters per second, and we know theta is 19.5 degrees. We don't really have a lot more information than that. So we want to solve for t. We need something to allow us to solve for t. The equation that we have that would allow us to do that is, take a quick moment, because I realize I never let y'all do this, and try to figure out which equation we should use on your own, and then I will tell you. So pause the video, try to figure it out, and then hit play when you're ready, or just keep watching if you're not sure. Okay, so this one is a little bit tricky because we're sort of combining a launch angle and projectile motion, which that makes sense that you would always be combining them. But that just means we're going to have to be careful with the equation that we choose, because we have quite a few to choose from. So let's use the one that's going to be the easiest for us to work with. And that one is the velocity in the y direction is equal to our initial velocity multiplied by the sine of theta minus gt. We're trying to solve for time. We have theta, we have our initial velocity, we know what gravity is. But what about this velocity in the y direction? Well, we've been given a very important piece of information in this problem. And it says right when that water hits the beetle, it is moving horizontally. That means that it does not have a velocity moving upward. That does not exist. No, it is only moving in the x direction. So we can simply set Vy equal to 0. And we can start plugging in what we know, which would be 0 equals 2.30 meters per second multiplied by the sine of 19.5 degrees minus 9.81 meters per second squared times t. Okay, now that we have all of that in, we can solve and rearrange, and when you do, you should find that t is equal to 0.0783 seconds, and that is the correct number of significant figures, 1, 2, 3. Whew, okay, now that was part A. Let's try part B. I'm going to erase all of this. So we have time, 0.0783. Time is 0.0783. Okay, so for part B, we want to know the height of the beetle. Okay, maybe this one will be just a little bit easier. So, I'm sorry, this is taking too long. Okay. Time is 0.0783 seconds. This could be useful for us. So what equation might we use for part B? Go ahead and see if you can identify it. All right, well, height is just that y value. So it's that value right here. So I hope you chose something that starts with y equals. And in this case, we want to use y equals v naught sine theta multiplied by t minus 1/2 gt squared. When you plug in all of the necessary information, and this one's very straightforward, we have everything, you should find that y is equal to 0.0300 meters. And we added those 2 extra zeros because we needed 3 significant figures. And the final one, we want to know the distance between the fish and the beetle when that water is launched. So go ahead and give that part a try and press play when you're ready. Okay, so for the horizontal distance, that just means x. So we're looking for x. An equation that allows us to solve for that is x equals the initial velocity multiplied by the cosine of theta times t. When you plug in all your information, you should have found that x is equal to 0.170 meters. And I hope that is starting to make more sense now. And that brings us to the end of the Chapter 4 lecture. So we've covered motion in 2 dimensions and free fall. Free fall in terms of launching things from a particular angle. So now that we have completed that, there are some study guide questions that I highly recommend y'all try to work before attempting the quiz. Again, if you have any questions, please don't hesitate to reach out to me. Post in those discussions so that maybe a classmate who is understanding things can offer a solution. And then again, when I see that no one seems to know the answer, I will happily jump in. But enjoy the rest of your day, and I'll see y'all next time.